Dear students, in this video we are going to discuss about single step impedance matching. Impedance matching is very essential when we are using the transmission lines at high frequency. If the impedance is not matched perfectly with the transmission line, the effective power transfer cannot happen. So in order to avoid this kind of problems and to avoid the standing waves, we used to go for impedance matching. So in impedance matching, so we are having two category. One is single step impedance matching and another one is double step impedance matching. So today we are going to talk only about single step impedance matching. Just look at the given problem. It is given that RF transmission line of 100 ohms is terminated with an impedance of 40 plus J30 ohm. Determine the stub length and position for matching the impedance. For single step matching, uh, we are having two different solutions. One is the analytical method and another one is the graphical method or using the Smith chart. So in analytical method, we used to determine the stub distance as well as the stub length based on some mathematical calculations. Whereas in graphical method or in Smith chart, it doesn't involve such mathematical complexities. So in a simple manner, we can be able to determine the stub distance as well as the stub length. So first have a look on the analytical method. The stub distance is given as Ls equal to lambda by 4 pi into pi plus pi minus cos inverse of modulus of k. So where lambda is the wavelength and pi is the angle of the coefficient and k is the reflection coefficient. The stub length Lt is given as Lt equal to lambda by 2 pi tan inverse of square root of 1 plus modulus k square divided by 2 into modulus of k. And we know that the reflection coefficient k is given as k equal to Zr minus Z0 divided by Zr plus Z0, where Zr is the load impedance and Z0 is the characteristics impedance. In this problem, we have Zr equal to 40 plus J30 ohms and Z0 equal to 100 ohms. We can determine the value of the reflection coefficient. So just substitute the values of Zr as well as Z0 so that you will be getting the reflection coefficient. So here, first we can convert the rectangular coordinate systems into a polar coordinate so that you can easily find out the reflection coefficient. So we are getting k equal to 0.468 with the angle 141.335 degree. So the magnitude of k is 0.468 and the phase angle of this reflection coefficient is 141.335 degree. Now substitute the value of modulus of k and phi in the equation of the stub distance Ls. So by substituting the values, you can get Ls equal to 0.36 lambda. Now let us determine the value of the stub length. So just substitute the value of k in this equation and you can find Lt equal to 0.138 lambda. Okay, so if the frequency is given, you can find the value for lambda and you can substitute. Otherwise, you can simply put as lambda. Position of the admittance. Now we have to move this admission point clockwise on the S circle. So where the S circle is intersecting the unit circle, that is R equal to 1 circle. So up to that point we have to measure the length. So that will give the stub position, and at the matching point we can measure the susceptance. Now the next step is to locate the negative value of this susceptance on the outer circle, and this point can be connected with the center point. So the distance between r equal to 0 and this new susceptance point will give the step length value. Now let us start with this Smith chart. So first step is to find out the normalized load. So ZL equal to 40 plus J30 divided by 100. So that is equal to 0.4 plus J 0.03. Sorry, 0.3. So now through this real part, so 0.4 is here, and move through this circle, and imaginary part we are having positive value, so you have to look on the upper side. So you just go through where we are getting 0.3. So and this is 0.3, and just put the mark the point where this 0.4 circle and this 0.3 reactant circles are meeting. So that will be your load impedance point. Now with the radius between this point 1, that is center point, and the load impedance, draw a circle, and this circle will be called as the impedance circle or constant S circle. Now next step is to find out the admittance. So for finding the admittance, just extend the line from this impedance point to the opposite side through this center. So this is a point where this line is intersecting with the constant S circle. So that point will give the load admittance, and from here you can see that. So this is the real part corresponding to this point is 1.6, and the imaginary value is 1.2. So this imaginary value we are getting at the bottom side. So this will be provided with a negative sign. So the admittance YL equal to 1.6 minus J 1.2. So now we have located this admittance. Now we can see the position at the outer circle, right? So the next step is we have to move this admittance from this point to the matching point. So the matching point will be obtained where your constant S circle is intersecting with the R equal to 1 circle or unit circle. So that point, you know, we have to determine. We got the value of LS. Now next we have to find out the stub distance. For finding the stub distance, we have to measure the susceptance at this point, right? So at this matching point, what is the susceptance we are getting? So that we have to see. So that is around 1.1, right? So we have to get the opposite value, that is minus 1.1 we have to get. So that obviously you can find at the bottom side. Okay, so now we have moved this, and we have determined the stub distance. Now we are going to find out the GB value, that is here for this case we are getting it as 1.1. Now the negative values, that is minus 1.1 we have to mark. So that is here, right? So now draw a line from this origin to this point. Okay, right? So here you can find the position, and the distance between this point to this R equal to 0 point will give the stub length, right? So at this negative susceptance, the position is 0.368 lambda. Now you have to find the distance between this 0.368 lambda and this r equal to 0 value, that is normally represented by 0.25 lambda, right? So this distance you have to measure. So stub length is given as LT equal to 0.368 lambda minus 0.25 lambda. So you will be getting the value is 0.118 lambda. And we can see that in analytical method we got this as 0.12 lambda. So almost same value we are getting. Okay. So it is 0.12 lambda. Now after getting these values, so you have to draw the schematic of the transmission line with load and the short circuit stub. So LS, here you have to mention the stub distance value, and here you have to mention the stub length. So in this problem they haven't given the operating frequency, so we have given in terms of lambda. If frequency is given, then we have to calculate the value of lambda and you have to multiply that value, and we can represent the distance either in terms of meter or centimeter. Okay, so thank you. Hope it will serve its purpose. So thank you.